All right, our next topic is that of special random variables. So in this case, we have situations where they meet some type of profile or prototype, and if we meet the characteristics of these prototype, then we have all of the probabilities already available to us in the form of tables, and we have formulas for the expected value and the variance, and we have some other time-saving techniques. Our first special random variable is called the binomial distribution. And as always, we start with an example that illustrates what it is we're trying to learn, so we can get a foothold, a grounding on what it is that we're dealing with, so it makes sense. Our problem concerns Eager Beaver, a salesman for Planet of the Grapes, a medium-sized winery near Solvang. He's going to do a sales trip for 10 restaurants throughout Southern California. Historically, Igor convinces 30% of the restaurants to stock his wine after he makes his sales pitch to them. So, letting X be the number of deals he closed on his upcoming trip, what is the sample space? So we got a random variable. How many deals he will close is a number. It's uncertain, it's a random variable. And how many deals will he close out of 10 customers he calls on? Either 0 or 1 or 2 or 3 or up to 10. So it is definitely discrete and it's finite. And it turns out it follows a distribution known as the binomial. And what is the binomial used for? When we have people coming in with appointments. Like we do here, we have appointments for 10 customers. So I know how many customers I got, and then I got a close rate. Each of the customers I close with probability 0.3. So historically, I've closed 30% of the deals I've pitched on. If we determine that it is binomial, so this is a series of tries. Each try results of 1 or 2 possible outcomes. That's where the bi comes from. And we have 10 tries. Each try we got a 30% chance. Then the number of successes we will get is a binomial distribution. Its expected value is given by this formula. Once you determine something is binomial, you need to specify 2 what are called parameters. Parameters for the binomial are n, how many tries did you have? And p, what is your probability of success on each try? What's our expected number of successes? It's given by the formula NP, 10 times 0.3 or 3. We didn't need to take this class to figure that out. You got a 300 hitter, 10 at bats, or you got Shaq. What was Shaq, about a 30% free thrower? No, he was actually better than that. At 10 tries, how many do you expect him to make? 3. Yeah, makes sense, and it matches our intuition. What we didn't know is the variance is given by the formula n times p times 1 minus p. That would have taken us several hours to figure out for this particular case what the expected value is. Maybe half an hour of Excel. That saved me a lot of time and effort. I don't know what the variance means, but the variance for this random variable is 10 times 0.3 times 1 minus 0.3, or 10 times 0.3 times 0.7, or 2.1. The next thing we look at is the probability of specific. All right, so we're ready to take a look at the probability of specific events, and we do have tables to help us with that endeavor. We have the binomial tables, which are provided for you out in a Canvas. It's one of the tabs is called Workbook Tables. You will need a hard copy of those tables for the midterm exam. If I want to know what's the probability that we close 0 or 1 or 2 or 3 or 4, in other words, 4 or less deals. That is a direct table lookup. less than or equal to is our direct table lookup in the tables, the probability tables that I've supplied for you. So we would head back to our tables and we would go to the binomial table, which is on the first page of your tables. And we see our first argument is n. We need n of 10. So that takes us to the third page of the tables. The next argument we need to use these tables is what is the probability of success? That gives us the column. And that's stated to be our success rate was 30%. And then we wanted 4 or less. So there's our probability right there, 0.8497. That is in the row labeled 4. So given a binomial distribution with n of 10, p of 0.3, the probability being 4 or less is 0.8497. And that is what is supplied here. So it's a 0.84 and 84.97% chance we will close 4 or fewer deals. So it's on the third page of binomial in the 10th row, in the N10, in the X labeled 4, and in the column labeled 0.3. And that's indicated by the shaded area here. Okay, what else can I ask you about the probability of various events? I can ask you probability being less than or equal to something. And the word that says that is 4 or less. No more than 4, that would also indicate. If I said between 2 and 4, it means very specifically 2 or 3 or 4. How do I find probabilities for between? Well, I take, and into my hat, I want 2, 3, and 4. Into the hat, I drop what? 0, 1, 2, 3, and 4. That's what I dropped in the hat just then. 0, 1, 2, 3, and 4. What do I want to get rid of? My brother-in-law. 0 and 1 I want to get rid of. 1 or less gets rid of those. I want to keep 2, 3, and 4. So if I take 0 through 4 and get rid of 0 and 1, what's left in the hat? 2, 3, 4. So anytime I ask you for ranges, you take the high value, look up the probability of being less than or equal to that. You take the low value, drop it by 1, because you don't want to take out this bottom value. You want 1 below it. The next thing I could, I guess we should look that up. So looking up 1 on here. There we go. Hopefully it's, oops, wrong. There we go. 0.1493 is the appropriate value. We got that. Yep. Did good there. If I say exactly 4, what's the probability we closed exactly 4 restaurants? Okay. Well, how do I get equal to 4? I could take 0 through 4 and put it in a hat. And I could take out and remove 0, 1, 2, and 3. What's left in the hat? 4. That's how we do exactlies. Okay. So it turns out that the cumulative distribution is the most efficient way to provide your tables. Because with the less than or equal to's, we can find anything. I can find less than or equal to's, I can find ranges, I can find equal to's. And it turns out I can use those very quickly to find greater than or equal to's, which is of course our next one. So if I want to know what's the probability exactly 4, I put 4 in or less in the bucket and put 3 or less, remove 3 or less from the bucket. And then 0.6496 is of course in our tables, and right here for 3. And then the last thing we can do with the tables is at least 5. What is the probability that we close 5 or more restaurants? Well, I don't have a table for greater than or equal to, but I don't need one. Using rule 1, what's the complement of 5 or more? 4 or less. So I start with 1. What did I put in the hat with that? all of them. I dropped all of them in the hat. You could say probability X less than or equal to 10. That would have worked too. But on our next special random variable, the upper bound is infinity. So that ain't going to work in general. But 1 always works. 1 puts all of them in a hat. I want 5 or more. I put all of them in a hat and remove 0, 1, 2, 3, and 4. What's left in the hat? 5, 6, 7, 8, 9, and 10 in this case. So that would be 1 minus what we got on the first example we did. So that's how we use our cumulative table. So if we determine that something is binomial, it's great. We got a formula for the expected value. We got a formula for the variance. We got tables to look up probabilities. The binomial is our friend. It makes things go much quicker. We want to see a lot of binomials on the midterm. Will I tell you that it's binomial? Of course not. I will not insult your intelligence by doing that. I will expect you to read the problem and figure that out. Yeah. How do we actually implement strategies for the binomial? Eager wants to give each client a gift, that he closes a gift. How many gifts should he take on the trip to be at least 99% sure he's got enough? When I actually go to implement this probability theory in the real world, I end up using the cumulative distribution because we will be given optimal percentiles. Here we're told whatever the reason is, our optimal percentile is the 99th percentile. Stock at the 99th percentile. All right, let's see how easily that's accomplished. So I head to this table here, and here's my cumulative. It starts small and goes to 1. And I look down this table and say, where's the first one bigger than or equal to 0.9? Oh, there's the closest one, let's use that. You don't grab the closest one to 0.99, you grab the first one bigger than or equal to 0.99 to get the correct value. So that's the first one bigger than or equal to 0.9900. It is 0.9984, and that's in row 7. Stock 7. Take 7 gifts on your trip. Okay, it is the first one bigger than or equal to. When you look up percentiles, we pick the first one bigger than or equal to. And then the final part of this question says to go into Excel and using one of the embedded functions in Excel, plot the probability distribution for the binomial. Okay. So if you go into Excel, and here I put the values that the random variable can take on in my column here, 0 through 10. If you call a binomial function like I did here, I have for the row 4, I've done the binomial function, and this is for the probability distribution itself. This is the probability that we will sell exactly 4, let's close exactly 4 restaurants. Here's a probability we'll close 0, here's a probability we'll close exactly 1, probability we'll close exactly 2, 3, 4, and so on. And since it is discrete, we get blips. We get a probability here, we got a probability here, probability here, probability here, probability, boom, boom, boom. And we get a rough curve that looks like a ski jump, huh? A ski jump facing the right. This is referred to as skewed to the right, as we'll see in the second half of the course. Don't worry about it now, but if you want to learn it now, go ahead. Skewed to the right. And we see our distribution. Here's the one with the highest probability. That's 3, and so on. Now to call the binomial function, so what did I do for this particular cell right here? Okay, I say equal, B-I-N-O-M. Give me the binomial dot distribution find me the probability for whatever's in A6, which was 4, given that n is 10, p is 0.3, and false. What is that? Okay, Excel is not very user-friendly in this regard. It says, do you want the cumulative distribution, true or false? False. No, I don't want the cumulative. The one we use most often is the cumulative. That's why its default is that you want that one. But no, I don't want the cumulative. I want the individual, the equal to values. And we get a distribution like that. If I ask you to plot the cumulative, this is the exact same, this is a plot out of this column, right out of the table. To do the cumulatives, there's a probability of 0 or less, 1 or less, 2 or less, 3 or less, 4 or less, and so on. You do the exact same thing under, except when it comes to which, do you want the individual terms or do you want the cumulative? I say true, I want the cumulative. And we get a shape of a curve like this. This is a stretched out S curve. This is called an ogive curve, as we'll also learn in the second half of the course. This is called an ogive curve. Any curves that look like stretched out S's are typically called ogive curve. Now, will I ask you to do this on the midterm? No. So immediately take it out of temporary and permanent memory. But you know, when you get out there in the whole cruel real world, you may need to use the binomial distribution. If so, please review the notes. That's what I'm here for. Now let's backtrack and see what went on here. The binomial distribution was developed by one Jacob Bernoulli. He was a Swiss mathematician. He was, I think, in the 1600s. He was not a kind person. He was kind of like me, a real jerk. Here's his picture. Real sweet looking fellow. See that? He looks like he's sucking on a lemon in that picture. This is him on a happy day. Okay? This is me. This is me right after this class ends. Sorry. All right, so why was he an unhappy person? Well, under any normal circumstances, he would have been the smartest man in the world during his lifetime. But unfortunately, he got pillared between Isaac Newton and Leibniz. Leibniz, I think, another Swiss mathematician, and of course, Isaac Newton, a famous English mathematician, physicist, and genius in any number of subjects. And under normal circumstances, he would have been the smartest guy in the world. And he was either third or fourth at the time. And who was the person who was third or fourth with him? His brother, Johann. Okay, and in the beginning, they collaborated, but shortly after collaborating for a year or two, their egos got in their way and they didn't like each other and they hated each other eventually. And unlike my relatives, which at parties we get drunk and we physically assault each other, their thing would be to intellectually humiliate their brother. They would pose mathematical problems and defy their brother to solve them. Solve this, mother, basically. And true story. And so Jacob Bernoulli was from the Bernoullis were very smart, and the whole family was smart. He had a nephew named Daniel who's exceedingly smart. He was the smartest man alive during his watch, Daniel. Much like the Darwins, Charles Darwin was not the only smart Darwin. His grandfather was exceedingly bright. Had a nephew won a Nobel Prize. So the whole family was bright. Besides being a jerk of a person, he had good DNA. Jacob did. All right, back to the ranch here. So we got the binomial distribution developed by Jakob Bernoulli. Jakob Bernoulli, besides developing the binomial distribution, was the first one to prove the law of large numbers, and he proved it for this particular distribution. He was also one of the first people to use the idea of probability as a scale of our uncertainty and use the scale from 0 to 1. So he was a truly gifted person. And he got stuck between Isaac Newton. Isaac Newton, probably the second smartest person who's ever walked the earth. He invented calculus. He did all of classical physics. He did things with light. He predicted the photon before Einstein proved the photon. And and the thing was, he only did it in a like 10% of his work effort. He spent 90% of his time doing what? Working on alchemy, trying to make lead into gold, and trying to decode the Bible. That's how he spent his other. If he would have actually, concentrated on science, he would have been 400 or 500 years ahead of his time. But the way it was, he was like 100 years ahead of his time. So if we have a binomial developed by Jakob Bernoulli, we have a series of tries. Each try results in a success or a failure. Okay. N is the number of tries. P is the probability of success on each try. Our sample space takes on the values 0 through n. Okay, what's the formula that Excel uses to get the probability distribution? It's that. Leave that open on your notes at your dinner table for mom to see. She'll be impressed with that. What is this? Is that a surprised n? What is that? I have no idea what that is. Yeah, I know what it is. But do I need this? No. Excel's got it. That's what it uses to, when you call that binomial true, that's what it's using. The exact formula it's using. Here's the expected value. Here's the variance. Less than or equal to. Look it up. Range. Take the upper bound. Look that up. Take 1 minus the lower bound. Look that up. Equal to. Take it. Look it up. Less than or equal to. Take 1 minus that. Look it up. And greater than or equal to. Like that. So that's our binomial distribution. And how do I know when I get a binomial distribution? Well, first, you got a special case. If I go back to this problem, I read the problem and what? There's no series of frequencies or probabilities given. So it's not the general case, it's one of the special cases. And you got to figure out what it is. What makes the binomial unique? The sample space takes on the counting numbers, and it is finite. 0 through 10. That will make it unique for the special random variables. It takes on the counting numbers, and it has an upper bound. Let's look at our next special case. And it's now 8 a.m. Monday morning, and Ivana Dye has just arrived at her job as an IT troubleshooter at a small corporation. Ivana spent the weekend at a bachelorette party in Vegas for her best friend who's getting married. Ivana has a horrible hangover. I have no personal knowledge about this. And must work until 12 noon before she can seek relief. One of those hangovers where you can feel your cells divide. Ouch, ouch. Never mind. Trouble calls come into Ivana randomly at a rate of 2 per hour. What's the probability that this morning she will get X number of calls? So she's got to make it 4 hours. She's got to suffer through 4 hours agony before she gets relief. And we want to know how many calls are going to come in to the switchboard in the next 4 hours. All right, I'm not giving anything else. So I'm not giving any frequencies or any probability distribution. It's got to be one of our special cases. First off, what values can it take on? How many calls might come in this morning? Oh, 0 or 1 or 2 or 3. I expect around 8, but could be 9 or 10 or 11. Any upper bound? No. You say, well, there's 100 people working in the company. Yeah, but it's the same idiots calling over and over and over again, with a problem. So no, that doesn't, yeah, can we handle an infinite number in 4 hours? No, but there is no specific upper bound. There is no specific upper bound. They just get less and less and less frequent, but there's no cutoff point per se. So this gives us the characteristic of the Poisson distribution. The value it takes on are the counting numbers 0, 1, 2, 3, 4, 5, no upper bound. That distinguishes it from the binomial right then and right there. If it has an upper bound, it ain't Poisson. If it doesn't have an upper bound, then it ain't binomial. So you know those. So I want to know how many calls we get in the 4-hour period. Okay, this is derived by a French mathematician known as Poisson. Not Poison, it's called Poisson, it's French. When you go to a French restaurant and you see Poisson du jour on the menu, what's that mean? Fish of the day, Poisson du jour, fish of the day. So there was a French statistician, we'd call him Fish, right, who developed this distribution. Poisson du jour, fish of the day. Poisson has 2 parameters. You got to tell me what's the average rate of occurrence, average rate of arrival, and the problem says they come in 2 per hour. And then you got to say, how long am I going to observe this process for? And Ivana needs to know how many are coming in the next 4 hours, to figure out whether she can survive or not. So if we determine that something is Poisson, what is its expected value? Expected value is given by lambda. Lambda is the first argument, I forgot to mention that. Lambda is your average rate of occurrence, or your average rate of phones coming in or arrival. And T is the number of time periods you're going to monitor it for. The expected value is given by lambda T. Well, lambda is 2 per hour, 4 hours, 8. I would not need to take this class to figure that out. But I would need to take this class to figure out that it's also the variance. The variance for the Poisson is 8. For this particular example, it is one of the few distributions that have the fairly unique characteristic that the value which measures its long-term average also measures its variability. So now you have something to talk about at the next business mixer, huh? Wonder why nobody ever talks to me at the mixers. I think I know why. Now, what's the probability? X less than or equal to 10. What's the probability? She'll have to suffer through 10. Maybe that's her limit before her head explodes. 10 or fewer calls coming in to the helpline. Well, what we need is the Poisson distribution. We keep going down our tables until we, oops, went too far, until we find something that starts to smell like fish. And here's our Poisson distribution. And we need a lambda T value. Our lambda T is 8. And we get the lambda T of 8. Here we go. Here's all the value we need right there. That's the cumulative distribution for the Poisson when lambda T is 8. 10 or less, bingo, 0.8159. 8159. Between 6 and 10. Ooh, that's a range. Ooh, works just like the binomial. I take 10 or less, put it in the hat. I want 6 through 10. Get rid of, take out of the hat, minus 0 through 5. What's left in the hat? 6, 7, 8, 9, 10. Okay, so that's our target. And we grab them all, 10 or less. Everyone's 10 or less gets all the ones I'm concerned with, and get rid of the undesirables. Okay. My brother-in-law, his wife, and the 3 kids. This is therapy for me. 10 on the button. Take 10 or less, subtract 9 or less. Got it. 11 or more. 1 minus 10 or less. That's the Poisson distribution developed by Simone Denise Poisson. Okay. And he was, as I said, a French mathematician. He was challenged with estimating the, I think it was challenged with estimating the population of, I think, Paris. And that depended on births and deaths. Births happen randomly over time, and deaths, birth and death both happen randomly over time. And so that's how he was interested in deriving this particular distribution. It has 2 parameters, lambda and t. Lambda is the average rate of occurrence. T is the number of time periods we're going to watch it for. And we count things as they happen. So as they happen, there's 1, there's another, 0, 1, 2, 3, 4, 5. The sample space is discrete, but it has no upper bound. Technically, we call it infinite. Here's the that's a complex looking formula. Maybe use that one this week instead. That's what, of course, Excel has in its library when you call the Poisson function. Expected value variance, same thing, lambda t. And the rules for finding less thans, ranges, equal tos, and greater thans, exactly the same as the binomial. All right, today in business statistics, we're offering our 2-for-1 sale. 2 distributions for the price of 1. Whenever you get a Poisson, you also get an exponential. It's a different way of looking at the same process. It's a different way of looking at the same thing. So what are we looking at? We're looking at calls coming into the switchboard. And what did I do? I set an alarm clock for 4 hours, and to get the Poisson, I counted them as they came in. And when the alarm rang, then I stopped counting. Another way to watch this process would be to what? To time how long it takes each call to come in. To time, figure out the time between calls or time until the next call. Same thing. And that's what the exponential is. Whenever we have a Poisson, okay, we also get an exponential. If on the midterm you see a problem that says something, something, something occurs randomly at a rate of 10 per hour, you know right now it's either a Poisson or an exponential. If we count, it's Poisson. If I get out a stopwatch and measure the time until the next occurrence, it's exponential. Okay? So as soon as the problem says something occurs randomly over time or something along that, then it's either Poisson or exponential. If we count, Poisson, measure the time, or the equivalent of that is exponential. So the notation, t, the time until the next call. Okay. But before we do that, let's just do some examples. So I told you the binomial was used whenever we know how many potential customers we have, and then we're going to give a pitch to, and then we have a certain close rate. So when people are coming in with appointments, a lot of times we see the binomial. If they're coming in without appointments, then we see the Poisson. The Poisson's the #1 distribution for modeling behavior in retail retail outlets or in the internet. On the next order going to come in across the internet, basically Poisson, or how many orders will I get in the next 2 hours is Poisson. How long before the next order comes in is exponential. So we got 3 things going in. The binomial is how many successes we had in n number of fixed tries. Again, people with coming in with appointments, binomial. Without appointments, Poisson, and then the time between the orders, coming in without appointments, exponential. They're classic cases. Let's play the latest game. What distribution am I? Let's practice for the midterm. Let's get used to figuring out what distribution is it. The number of customers coming into a store in the next 24 hours. Shh, 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 shh. Don't say anything. I'm thinking. I'm becoming a sea-sun sloth. Slowly thinking about it. The number of customers entering a store in the next 24 hours is... Good grief, I've lost the hearing in both ears. Oh, I tricked you up. You can't just sit here and sleep. Somebody go out on a limb. Somebody other than the person who called out exponential. Poisson. Oh, I love it when you talk French. It is Poisson. Remember the Addams family? Remember the Addams family? What was the guy in Addams family? I forget his name. Anyway, he'd go nuts when his wife talked French. It's Poisson because what? Well, first off, can it take on the value 1.234? No, it's not exponential. Okay, so it takes on the counting numbers, right? 0, 1, 2, 3, 4 customers come in. Does it have an upper bound? No. Poisson. Got it? Let's try it. Let's try it again. The time before the next hit on our website. Think about it, think about it, think about it, think about it, think about it. Go ahead, say it. I know it. Exponential, correct. Can it take on the value 1.234 minutes? Yeah, it's continuous. Okay, end of story. The only thing we've seen so far that's continuous is exponential. Don't need to go any further. Can it take on the value 1.234? Yeah. Done. Exponential. The lifespan of an electronic chip. Let's think about it before we answer. Let's be a sloth. We get slow and methodical. Can it take on the value 1.234? Can it take on the value 1.234 years? Can my chip last 1.234 years? Yes, it can. It is. It's continuous. It is exponential. Right then and right there. It is exponential. Don't need to go any further. Can it take on the value 1.234 years? Yes. And the lifespan of electronic chips is exponentially distributed. You want to know how long your chip lasts? Use the exponential distribution to do that analysis. Doing so well today. My progress report to your parents is going to be so glowing. Okay, the number of freeway fatalities in LA County next month. Shh, shh, shh. Don't speak, think. Okay, speak. Thank you. Poisson. Weak, but a sign of life there. Poisson. Can it take on the values 1.234 deaths? No. How many deaths? 0 or 1 or 2 or 3 or 4 or 5. Is there an upper bound to the number of people who might die? No specific upper bound, no. Poisson. And finally, the number of defects in a box of 50 parts. Can I take on the value 1.234 defective parts? No. Is there an upper bound? Yes, it is. It is. It has an upper bound. It has an upper bound. Binomial. It has an upper bound. Oh, but I wasn't talking about binomial right then. I'm sorry. It's binomial. All right. So, this is practical stuff. Nope. All right, so let's go back and learn the exponential distribution, how to work with it, and then we're out of here. So, where were we? I was Ivana Dye. I was sitting in here in my job watching these people mess up and call me for technical assistance. The calls are coming in randomly. And I want to sneak out and get something to drink. I want to know, if I'm gone a half hour, what's the probability I'll be missed? Okay, that somebody will call for me in the next half hour, for example. Okay. So I want to know how long before the next call comes in. Okay, what values can it take on? Well, when can the next call come in? This instant or any instant in the future? How do I write that? Here's how we write this instant or any instant in the future. That's how I write it. It's anywhere between now and sometime in the future. And it is our first distribution. That is continuous. Okay, we're looking at the same process, right? Calls coming in, so it's got to have the same parameter, which it does. They come in at 2 per hour. What's the expected time until you have to wait to see a call comes in? Okay, it's 1 over 2. Okay, since they're coming in 2 per hour, what? They come in every half hour. Makes sense, huh? That's what it just told me. The expected time we have to wait is half an hour. What's the variance? I don't know what that means, but the formula is 1 over lambda quantity squared. I want to know what's the probability that we get a call coming in with the next half hour, for example. Less than or equal to? Obviously, what do? Just look it up. Every table we have is a less than or equal to table. They all work identical to each other. Okay, so I head to the exponential distributions. How much did we pay for this table? How much did we pay for our workbook? Nothing? Grief. No wonder he's dressed like a pauper. He's going broke. All right, eventually we find our, on page 11 of our tables, the exponential distribution. And I need a lambda t value. Oh, I go back and say, all right, get me a lambda t value. Lambda is 2. And you want me to look at 0.5 or less? 0.5. I need 1.00 is my lambda t value. I head to my table and I go 1.0. That looks good so far. All right, what's this? What's this stuff here? I don't know. Well, this is my hundredths digit. 0.10 what? 0.109? No. 4? No. 1.00? Oh, okay. That's it. 1.00. And I get 0.6321. Okay, I know some of you missed that. Okay, but what we have here, I'll give you another example in a minute that'll clarify it. When we have a continuous random variable, we can't talk about the probability of each specific point, because when I add up an infinite number of them, I always get something bigger than 1. So what we go with is area under a curve. So which probability now becomes an area under a curve. And here is the formula, here's the curve for this formula for the exponential distribution. And the probability of being half an hour or less is this area right here. And that's 0.6321. Total area under the whole curve is what? 1. Total area under the whole curve is 1. This will help in your use figuring out how to use the table. What if we wanted to know what's the probability that something will come in within the next 0.56 hours? Don't know why I'd be interested in that, but let's just do it. Well, lambda is 2 and t is 0.56. Multiplying, we get 1.12. We head to our table, and here I go with 1.1. That gets me to this row. 1.1, 1.10, 1.11, 1.12. There it is right there, 1.12. It is 0.6737. That's how we use the table for the exponential. Ranges. What's the probability that the next trouble call will come in between a half an hour from now and an hour from now? So into the hat, I put all the times that are an hour or less. And then from the hat, I remove, what's going on here? I remove everything less than or equal to 0.49? No, 0.499? 0.4999999. Oh, I can't write it out because it's 0.49 an infinite number of 9s. What do? It's 0.5. Has exactly the same area. Probability being less than 50 and less than or equal to 50 is absolutely the same area. One has this 0.5 right here. One has the area under that point. What's the area under a point? Infinitesimally small. Moral of the story is, on a continuous, you do not drop down. You'd be leaving out a chunk of the curve if you dropped down. No drop at all on a continuous. So we take this probability, and we the probability we have already, 0.6321, which is the probability being something happening within the next half hour. Then we look up the one for an hour from now. Our lambda t is 2 times 1 times 2.00. We head to our table, look up 2.00, and we get 0.8647. Okay, and what about the probability that the next call comes in exactly a half an hour from now? We say 0 or infinitely small. We never talk about the probability of a specific point. It's a good mind bender. Each thing has an infinitesimally small chance of happening, but something's going to happen with probability 1. Da, 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 da. Works for me. Okay, and you get into infinitesimally small, things don't make sense anymore. So we never talk about a specific point. I can talk about the probability being between 0.499999999 hours and 0.5000001 hours. Okay, I can talk about any narrow range you want, but we don't talk about specific points because they all have an infinitely small probability of occurrence. Ta-da! That lecture alone is worth the price of tuition, huh? Okay, so here's our practice problems. The midterm will be probably half special random variables, because we have 4 cases. They don't take long to do. You read them, you figure out what's going on, and you use your tables and your formulas. Have a great week. And